Hi everyone, my name is Sam, and in this episode we will learn how to implement the gradient of the energy into our program. We will consider this from a numerical and an analytical perspective. I should warn you that this episode is pretty technical, and aside from that, I also want to add a little disclaimer that the method that I use to calculate the force on the particles is perhaps a bit of an unorthodox way to do molecular dynamic simulations. For these simulations, I care about speed and accuracy of the specific model that we simulate, which is a 3-point water model. I don't care so much about generalizing to any molecular system, basically. So yeah, but anyway, let's dive right into it by considering what the gradient of the energy actually is. Let's have a look at this energy landscape. This is a bit like a real landscape, with hills and valleys representing the maxima and minima in energy. In our energy landscape, the z direction represents the energy, and the other two directions represent some coordinate of our system, for example, the x and y position of a particle. If we now put the system in a specific state, for example on that hill over there will be a certain force acting on it. We can find this force through the gradient of the energy. The gradient of the energy will give us a vector pointing up in the steepest direction of the landscape. In order to get the force, we multiply this vector by -1. But how do we obtain this numerically? Let's consider the gradient fully written out into its 3 components. For simplicity, let's look at only the x component. Evaluating the derivative numerically at some point, x0 in a function, involves evaluating the function of x0 plus delta x and x0 minus delta x, where delta x is a very small number. This gives us 2 values of E, from which we can calculate the derivative with the following formula. As you can see, this involves evaluating the energy of the whole configuration twice. To illustrate why this is a computationally expensive operation, consider a system of particles with long-range interactions. To calculate the energy of such a configuration, we will have to calculate the interaction of every particle with every other particle. Worse, if we would like to calculate the derivative of the energy, we would have to do this twice, each time with a small displacement delta x of the atom under consideration. In terms of calculations, this amounts to order n squared operations per particle per time step, adding up to n to the 3rd total operations per time step. Is there an easier way to do this that does not demand so much computational power? The answer is yes, if we take instead the analytical derivative, which comes down to deriving the force by pen and paper. Taking the derivative this way has the advantage that it saves the computer some work, and also that it is more precise. The downside, however, is that this calculation is a bit more laborious, mostly because energy is one-dimensional and forces are three-dimensional, so it involves a lot of operations to get to the right reference frame. So yeah, let's start with the most painful case, namely the short-range intramolecular interactions. As we have seen in part 1, the water molecules has 2 internal interactions, bond stretching and angle bending. The formulas for the energies are given in cylindrical coordinates, and they are relatively simple to take the derivative of. The cylindrical coordinate system consists of an angle, theta, a radial component, r, and the z-axis. In the case of the water molecule, theta runs in the plane defined by the hydrogen-oxygen-hydrogen triangle starting from the x-axis and ending at the axis defined by the oxygen and the second hydrogen atom. Finally, the z-axis points perpendicular to the plane of the angle. For our simulations, we need to transform the force vector components to the global Cartesian system. We do this by first transforming to the local Cartesian system, and then from here transform to the global Cartesian system. Let's relate the hydrogen atom to the local Cartesian axis. We put the x-axis along the axis defined by the oxygen and the first hydrogen atom. The y-axis is then somewhere in the plane defined by the hydrogen-oxygen-hydrogen triangle. The z-axis points out of the xy plane and is the same in the cylindrical and local Cartesian system. The force in the local cylindrical coordinate system transforms in the following way to the local Cartesian coordinate system. The angular components are due to the angle bending, and the radial components are due to the bond stretching. Now that we transformed to a local Cartesian frame, we can simply add the forces for the angle bending and the bond stretching on the first and the second hydrogen atoms. But what about the force on the oxygen atom? Well, we know that the total force on the molecule as a whole should be 0. We just add the negative of the total forces on the two hydrogen atoms. Alright, so now we have the total force in a local Cartesian reference frame. How do we transform it to the global one? For this, we first need to properly define our unit vectors of the local Cartesian frame, starting from the water molecule. We call the vector pointing from the oxygen atom to the first hydrogen atom R1, and we call the other one R2. We know R1 and R2 in terms of the global Cartesian system, and this is what will help us relate the local Cartesian to the global Cartesian system. The x-axis is easiest to define. This is just R1. The unit vector is obtained by dividing by the norm of R1. How do we get the other two? R2 is not at 90 degrees from R1, so we cannot use this to define the y-axis. However, the cross product between R1 and R2 points in the perpendicular direction, giving us the z-axis. We then divide again by the norm to obtain the unit vector. Now finally, the y-axis unit vector can be easily found by crossing x and z. Good, we have properly defined the local Cartesian axis. How do we transform to the global ones? Well, for this we will use the rotation matrix, R, which has 3 by 3 elements. It rotates a vector in the local coordinate frame to the global one. The rotation matrix can be written as 3 columns defined by the x unit vector, y unit vector, and z unit vector. These are the unit vectors that we just identified. So what did we win by calculating the force analytically? Apart from a higher precision for the short-range interactions, we can achieve significant speed up for the long-range interactions. Recall that we had to calculate every possible interaction of our system to find the gradient of our energy. If we use the force, we only have to consider the force on one particle under consideration. This saves us a lot of calculation effort and reduces the total amount of operations per time step to n squared. Before we cast this into code, I would like to add 2 additions to the code from the previous episode. The first has to do with how the position, velocity, and acceleration matrices are ordered. Previously, we said that we would fill the matrices first with hydrogen atoms and then end with oxygen atoms. We will change the order to a sequence of molecules. This means 2 hydrogen atoms, 1 oxygen atom, 2 hydrogen atoms, 1 oxygen atom, etc. We can do this using a for loop to define indices that transform the old configuration to the new one. We then return to the part where we initialized our array and add 3 lines where we rearrange them using our new indices. The second change has to do with the solver. We previously calculated the gradient of the energy in one big for loop over all the particles. We will now split this part into one loop for the short-range interactions and add a function for the long-range interactions. We also predefine the arrays for the forces on top of the solver. Let's code our short-range interactions. In order to make it more exciting, I added a green background, reminiscent of the glorious times of Windows 95. The function describing the short-range interactions takes as an input the position of all the atoms and outputs the forces in the x, y, and z directions. In the middle part, things happen. We first have to select our atomic positions from the input. The input vectors x, y, and z represent the positions of all the atoms. We select out the 2 hydrogen atoms from the molecule under consideration and then the oxygen atom. Next, we define our R1 and R2 vectors from this molecule. For this, we simply subtract the positions of the hydrogen and oxygen atoms. For example, the vector R1 that points from the oxygen to the first hydrogen is equal to the position of the first hydrogen atom minus the position of the oxygen atom. The R3 vector points from one hydrogen atom to the other. We now have to calculate the hydrogen-oxygen-hydrogen angle theta, and we do this by using the inverse cosine rule, using the norms of the vectors that we just defined. We are now ready to calculate the forces in cylindrical coordinates. These are simply calculated through the terms that were shown earlier, the derivatives of the energy. Here, AB refers to the angle bending, BS refers to the bond stretching, and H1 and H2 refer to the hydrogen atom under consideration. Note that the second angle bending force term is the same as the first one, times a conversion factor. We can convert these forces to the local Cartesian frame using these simple conversion formulas. Applying this gives us the vectors with the xyz components of the force. Having defined the forces in the Cartesian system, we can add them up such that we get a compact expression of the forces on the 2 hydrogen atoms. The oxygen atom is just the negative of these 2 forces. Alright, so now comes the second part of this function, which concerns transforming to global unit vectors. For carrying out the cross products, we use the cross function in Julia. We then set up the rotation matrix, which is simply x, y, and z unit vectors next to each other. We transform the forces to the global Cartesian reference frame by simply multiplying the rotation factor with the force vectors in the local Cartesian frame. This has to be done for the hydrogen and the oxygen atoms separately. As a last step, we want to output the forces as global x, y, and z components. This means we have to group them and slice them up in the other direction. Okay, this is what our total function should look like now. Amazing! Okay people, that was it for this episode. I hope y'all could follow along. In the next episode, we will program the long-range interactions using the GPU. So see you then!